Hello again and welcome to another edition of Newton's Third Tutoring. Today we're going to be going over a topic in physics of electricity and magnetism called electric flux. Now electric flux can be thought of as the electrical energy that is passing through an area, similar to a hydraulic situation where you've got a flow rate passing through a cross-sectional area to give you the volume flow rate. One can think of electric flux in a similar manner where you've got an electric field passing through a cross-sectional area. The units for electric flux are Newton per meter squared all over Coulomb. And we'll go ahead and write the equation for electric flux now. So the equation for electric flux we denote with this character here. It looks like an I with a circle through it. And that's equal to the integral, the closed integral rather, of the electric field times the dot product of the differential area. Now again, this area is the cross-sectional area that the electric field is passing through, and the units here are Newton meters squared all over Coulomb. So here we're looking at a problem where we're looking at electric field passing through a cube. This is a cube that has edge lengths of 1.4 meters. And we're going to be looking at four different situations where we've got four different electric fields passing through, and we want to see what the electric flux passing through the right surface is. So the right surface I'm going to show here in red. That's the right surface. We want to see the electric flux passing through that area. So we'll go ahead and start with A. So A shows that we have an electric field working in the I unit vector of 6. And that's units of Newton Coulomb. One thing to note is that the unit vector for x is I, for y is j, and then for z is k. So when you have an electric field working in the I unit vector, that is the direction of the electric field. So we'll go ahead and show the electric field in blue here passing through the surface. We'll show that it's passing through in the I direction. So again, this is 6. Another thing to note is that the area unit vector or area vector is always orthogonal to the surface that the electric field is passing through. Always orthogonal, meaning that the unit vector, we'll go ahead and denote that in orange, for the area is always perpendicular to your surface. So this forms an angle between the unit vector of your area and the electric field. So that forms an angle of theta. So when we go to look at the electric field, one thing to note is that the electric field is effectively your electric field times the cosine of theta, because that's what gives you the vector that is the same sense as your area. So you always have to incorporate that theta value into your electric field. So we'll go ahead and do that here. Let's go ahead and write the equation for electric flux. So the equation for electric flux is equal to the integral. And because the electric field is a scalar, we can go ahead and factor that out. So it'll be V times cosine theta dot product of the differential area. So further simplifying this, we have 6 Newton Coulomb times the cosine of 90 degrees times the area, which in this case is, since it's a cube of 1.4 meters, just going to be 1.4 meters squared, and that's your differential area. We can see that the cosine of 90 is equal to 0. So because of this, the entire electric flux will be equal to 0 in this case. Moving on to B, we'll go ahead and we see that there is a electric field working in the J unit vector. So this is a -2. So what we do is, because it's a negative, it means it's acting opposite the direction, in the negative direction of the y-axis. So we'll go ahead and show that in blue here. So we've got an electric field working in the opposite direction, and again, this is 2. So this forms another angle. We can see here an angle of 180. So if we go ahead and plug that in to our electric flux equation, again, we're working with 2 minus 2 J, that's Newton per Coulomb. So if we go ahead and plug this into our electric flux equation, we get V cosine theta dot product of the differential area. Further simplifying, we get 2 cosine of 180 times the differential area, which again in this case is just 1.4 meters squared. Further simplifying this, we get minus 2 times 1.4 squared, which is, work on my calculator here, which is 1.96 meters squared. And again, this is in Newton Coulomb. So further simplifying this, we get minus 3.92 Newton meters squared all over Coulomb. And that's the electric flux acting with that electric field. Moving on to C, we see that we have a electric field working in the I and K unit vectors. So we've got minus 3I plus 4K. So we'll go ahead and show that here. Again, this is working on the right side of the cube. So it's going to be working something like this. So that's minus 3I plus 4K. So if you haven't seen it already, anything parallel forms an angle of 90 degrees with your differential area. And anytime you have an angle of 90 degrees, the cosine of 90 is 0. So every time that there is an electric field working parallel to your surface, it's always going to be a flux of 0. So again, we look at the electric flux equation here. The integral of minus 3I plus 4K dot dA. As you can see, dA works in the J unit vector, or in the y-axis rather. So further simplifying, we'll see that you have minus 3 times 0, because there's no area working in the x-axis, plus 0 times dA, because there's no electric field working in the y-axis, then plus 4 times 0 for the k unit vector. So this shows us that we have an electric flux of 0. And then lastly for D, the question asks, what is the total flux through the cube for each field? Now, because of the nature of the differential area always working orthogonal to the surface, if you've got an electric field, so we'll go ahead and just draw this out real quick. So if this is our cube, here that we're looking at, if we have an electric field that's passing through, let's take for example, because the question asks, what is the total flux? So we're going to add all of this together. The total flux of the electric field. If we look at, for example, A, where it's 6, so let's look at A. A is 6 working in the I unit vector. So it's x, y, z. So if we look at this, you're going to have the electric field passing through this surface right here, and then passing through this surface here. Those surfaces are parallel to the ZY plane. So you can see, remember that the differential area is always perpendicular to the surface. So we'll have a differential area that is opposite on this plane, but then same sense on this plane. So effectively what that does is it gives you equal but opposite values for your flux. Effectively they cancel out, so you'll get a flux of 0 when you're passing through this cube. And the same is true for each of these electric fields. For J, for example, if we're looking at B minus 2J, the same situation is true, where you'll have your flux passing through this plane here, and then this plane here. And again, you have your differential area that is always opposite, or orthogonal rather, to the plane. So again, you'll get an equal and opposite electric flux, which will give you a total flux of 0. So this is true again for C as well. When you have I plus 4K, you will also get an electric flux of 0, or total electric flux. So this is total electric flux. So the answer to D, when they ask what the total electric flux is, the total electric flux is equal to 0 for this cube, because we're passing through portions of the surface where, because the differential area is orthogonal, we're going to get equal and opposite electric fluxes as we pass through this cube. So our total is 0.